Welcome back to the channel. Today we are going to start a discussion on the exceptional electronic configuration of chromium and copper. We are all well aware that the copper and chromium are having exceptional configuration on them, but we will understand like how is it possible, why is it needed that they are having the difference in their electronic configurations. So first thing is that we will understand electronic configurations by looking up to the different factors. First thing is that the order of electron filling. They should be considered that electrons occupy orbitals following energy levels and impacting the stability. The two factors should be considered that first the electron should be placed into the one where the lower energy levels are easy to occupy, which require lesser energy to fill in them. So it's the energy level. Next thing is impacting stability. It will be the one that it should be either an orbital should be either half filled or either it should be fully filled. It's like if we consider D, the D suborbital or D subshell is the one which will be like either if you place 5 electron into it or either if you place 10 electron into it, then it will be stable, otherwise it will stay unstable. So first fact is that in order to attain the stability, we have to consider energy level, which would be impacting the stability of the orbitals. Upper principle indicates that it is the systematic filling of the orbital. We should consider like how Aufbau principle gave us the idea that electrons should be filled into the certain orbitals. According to Aufbau, he stated that first you need to fill electrons into the lower energy level. Just like electrons should be placed into 1s orbital, you cannot directly jump to the 2s orbital, then gradually you have to move to the 2p. So accordingly, if we consider this factor in chromium or copper, there are some electrons who could be who are stable enough to be first partially filling the 3d orbital, then they would be jumping to the 4s orbital. Unique configuration of transition metals, we are well aware that they are contain the unique configuration because they contain the big number of electrons which will enable them to attain some sort of different colors on them, and we are very well aware that they contain distinctive colors which makes them different from the entire periodic table because they contain maximum number of electron. That big number of electron will be enabling them to fill their d orbital, and even within like when they fill their electrons into the d orbitals, partial and full filling of electrons may show variation in them. That will show variation in the colors of the colorful elements are the result of this thing. Stability of the half filled orbitals is the one. Half filled orbitals like in copper, chromium, they offer greater stability due to the symmetry. When it comes to symmetry, copper and chromium both are exceptional because both of them, into a case where a more symmetric distribution of their electrons would allow them to become more stable. The shift of one of the 4s electrons in both to the vacant 3d orbital will allow both the elements to a significant distribution of electron to become more significant. The more easy they can distribute their electrons, the more easy they can fill up to their suborbitals. It's quite fine for them to attain the stability. You should be clear with the first fact that the distribution of electrons should be symmetric. Either the subshell should be fully filled or either they should be half filled, having electrons into the each of the orbital. Maybe they can have 5 electrons in the d orbital, or maybe they can have 10 electrons in their d orbital. In this way we can stabilize them. Next factor is exchange energy benefit. Simply, when they are having identical spin, it led to the exchange of energy. And when the energy, when let's say one electron gets excited, and let's say other 4 electrons are in their ground state. Simply, that higher energy will be distributed to the entire area, to the entire shell, and in this way, the higher energy will be distributed. So everybody will be getting enough energy, so that higher energy will be compensated by sharing that energy to the other 4 electrons, and in this way an element can attain the stability. Likewise, Chromium's actual configuration is argon 3D and 4s1. Simply, it will allow 10 exchange ways versus 6 in expected. Obviously, chromium will be the configuration of chromium is neutralized, or you can say that it's applying the same rule we have been studying, that the electronic configuration will be stable if the electrons are distributed into either half shell, or like either a subshell will be half filled or either it will be full filled. So we can say that if there is an argon, it can fill up to 5 electrons into the D shell. However, 1 is given to the 4s. But we can say that since it's the rule of partially filled or either fully filled subshells, that is why electronic distribution would be balanced to attain the stability. Copper stable configuration is that copper's electron. Okay, so its electronic configuration is 3d10. Obviously, one is fulfilling rule number 1, that electronic distribution should be partially filled, and other is satisfying the rule, like for the copper, that electron should fulfill the 3d orbital. When it is fulfilling the 3d subshell, it means that electrons are stable now, and we are referring to the stable configuration of copper. Again, expected configuration of copper is that simply the chromium's expected configuration is when they came out to be is having 4s when it should have to be the 4s, but it is 4s 4 3d4, but at the end it is 3d5. To attain the partial stability, it is having a unique configuration, because it was expected that there are 5 electrons, there should be 4 electrons in the 3d orbital or in the 3d subshell, but actually there are 10. The stability of half-filled orbitals is obviously quite significant, that there are two basic rules. One is symmetry and other is either they should be partially filled or either they should be fully filled. Likewise, if we consider the stability of the fully filled electrons or fully filled orbitals, simply the more obviously copper is attaining that configuration that deals with the fully filled electrons, fully filled suborbitals. But when it comes to the chromium is showing the partial filling of orbitals. Symmetry is important because the more symmetric they are, the more stable they will be. They consist of the higher exchange energy concept. Exchange energy rises from the electronic spin alignment. The more properly they are more aligned, they are having the same spin, the more possibility of exchanging energy would be there. Copper's actual configuration could be amended so that we can find what are the factors who are actually impacting its stability. Likewise, we can see that what are the implications of the half-filled or fully filled orbitals, like why are they needed? The stuff behind this thing is that this factor will be decreasing the electron shielding effect. It will be reducing the shielding effect. When obviously shielding effect is reduced, electrons which are closer to the electrons will go closer to the nucleus. They will be receiving the attraction from the nucleus. Obviously, we know that nucleus is positively charged, and when nucleus is positively charged, it can strongly attract the electrons. For the sake of revision, shielding effect is when the electrons cover up the area between, when the electrons who are closer to the nucleus will shield or will reduce the attraction of nucleus who are present a bit away. So in this certain way, if electrons are equally distributed, we can reduce the shielding effect. So that will also be adding to the it will simply reduce the shielding effect. When shielding effect is lesser, nucleus can attract all the electrons with almost same energy. Lower energy level, electron moving closer to the nucleus result in the lowering energy level, which is energetically favorable. So it is also contributing a lot to the stability. Influence on chemical behavior. Simply, the stability of these configurations significantly influences the chemical behavior of the transition metal, because we know that the transition metals show colors, and the reason behind showing colors is that they are having symmetrical distribution of electron. When they all excited or de-excited at the same time, they will show colors. Symmetrical distribution of electron. Half-filled and fully filled subshells exhibit symmetric or balanced electronic distribution, which will contribute to their stability. Exchange energy concept is that more electrons are there to accept when they are in the identical spinning. They are spinning in the same direction. The energy will be distributed to the electrons, and in this way they can excite or de-excite at the same time. Chromium half-filled configuration. Chromium's actual configuration allows 10 exchange ways compared to only 6 in the expected configuration, because we are simply changing this configuration. The basic concept is of this entire discussion is that their configuration is variable. Why? Because they are simply lying on the partial or fully filled orbitals. In case of chromium, the configuration is that D shell is partially filled, which is having 3D 4S1. When it comes to the copper, its configuration is 3D10. So they are fulfilling both the basic rules: fully filled orbitals or partially filled orbitals. Recent studies on the electronic configuration states that when they use Auger electron spectroscopy AES transition, they reveal that though they result in a shift in the kinetic energy for different oxidation states of copper, enhancing or understanding its electronic behavior. And they state the same thing, that all this configuration results in the enhanced electron mobility. New copper compounds display improved electronic mobility, which will be indicating there's a potential application in the electronics. Definitely copper has been used in the different perspective or in the practical application, because it led to their ability to conduct heat or electricity. They would be leading to their stability as well, so we can rely on them. Exceptional electronic configurations. Copper's actual configuration deviates from the exception due to their stability factors, because this is the main basic significant element factor we need for stability of the half-filled orbitals is that chromium's half-filled d orbitals provide enhanced stability that will demonstrate the energetic behavior of favorability of the such configurations. Symmetric electron distribution states that they result in a half or fully filled orbitals that led to the stability, which would reduce the electronic shielding. When electrons shield, obviously they would be resulting in the reduction in the attraction of electron to the innermost shell due to their positive charges. Likewise, they result in the lowering of energy due to the distribution of the electrons equally. So here is the case study for the energy exchange in chromium. Like, how does that energy exchange takes place? If we compare the electronic configuration of the two, how is it possible? So the first case is that when it comes to chromium, its expected electronic configuration should be argon, having 3D4S with the 6 exchanges possible. Obviously there are 6 exchanges possible. There are 3 possibilities for the energy exchange processes. But when it comes to the expected configuration of the copper, its exchange for the energy is like they can make 10 possible exchanges for the same procedure. Actual configuration for chromium is 3D5 4S1, and it will allow 10 exchanges in actual. Earlier it should be like, if we go with the same expected configuration, there were only 6 exchanges available. But when if we change this configuration, if we rearrange the electrons, it can make 10 exchanges possible. However, when it comes to the actual configuration of copper, it can show electron with the 3D10 fulfilling the subshell D. It's like fully filled with pair of electron. It may 5 pairs of electron, having 10 electrons in total, by providing the maximum stability in the element. There are half-filled d orbitals in the chromium, which will enhance the symmetric electronic distribution. There are 5 electrons available in the subshell D. So obviously there are 5 electrons available. Everybody is having one electrons into them. So this is called as half-filled electronic configuration, or you can also call it as half-filled symmetrical electronic distribution. completely filled d orbitals, which will further enhance the stability. Obviously they are fulfilling the condition that the two possibilities are there: either there should be a half filled electrons or half filled subshells available, or either there could be fully filled orbitals. Likewise, when it comes to the chromium, there are 10 exchanges possible that led to the greater energy release. So, as much as there are 10 possibilities for energy exchange procedures, they would be sharing energy up to the 10 possibilities that will enhance the stability. Why? Because this is a process when excitation is going to be shifted equally to all the singly available electrons. Likewise, when it comes to the copper, they are already stable because they contain 5 pairs of stable electron basically. Now, they are stable for the chromium. They are stable due to the reduction in the shielding effect from electron layout. Since electrons are equally distant from the nucleus, every d suborbital or every d subshell, they contain equal attraction towards the electron. So, shielding effect would be reduced in this procedure. Likewise, there is a similar stability in the copper to be achieved through the reduced shielding effect. So gradually, shielding effect is hidden in both of the cases. Lower energy state achieved by the electron being closer to the nucleus. Obviously, when they are closer to the nucleus, even they are stable as well, they would be carrying lower state of energy, because the further they are, the higher energy they would be requiring to get attracted towards the nucleus. Electrons in the 3D subshell maintains equal energy levels, while when it comes to the exchange energy, it results from the identical spin electron exchanging. Basically, when they are away from the electron, energy exchange takes place, things are having identical spins or them, equal distribution of energy is there. However, they can exchange in a fine possibilities. Likewise, they contain for copper, they contain maximize exchange energy that leads to lower the total stability or total electrons. So when it comes to the maximum exchange energy levels, the energy exchange or the total energy will be fine to achieve, as well as decrease energy correlates to the possible decrease in energy when electrons are not in excitation, they're in their de-excited state. Obviously, decrease in energy states takes place. They can you can say that they are lesser energy is there, the electrons are feeling de-excited, and in this case, if somehow they contain some excitation in them, energy would be equidistant, it is equally distributed. That will be increasing the stability of the configuration, as well as the stable configuration preferred in the nature of the transition metals. So we need stable configuration so that excitation could be minimized and stability could be maximized. Exchange energy in the chromium, it reflects the stability in the transition metals. However, exchange energy in the it is critical for understanding the electronic behavior in the copper. Why? Because it is fully filled, its electrons are fully filled, like subshells are fully filled. That is how they can attain the, they are stable in their suborbital d. So the final conclusion for this thing is that that's it for the stability of copper and chromium. We have been studying that why the electronic configuration of these two elements are different, why are we really concerned with this thing. So we had made an analysis and we have figured out that there are two simple crackdown factors, that the symmetry, the more symmetric electronic distribution is, the more stable the element's configuration is. We are doing it to minimize the energy exchange when energy is equally distributed among the elements, among the subshell, the more stable they are. So we can say that the stability is inversely proportional to the electronic distribution. The more the more fine way they are distributed, the more better way energy will be. The more pairs are there, the more fine way energy will be distributed at the least excitation, would be resulting into the stability of the electron. In the copper and chromium. So we are concerned with these two factors because we are deviating from the actual expected energy distribution, because we want to attain the stability. In that configuration, the expected configuration, the stability would not be possible. Why? Because electrons are not finally distributed. When they are not finally distributed, they keep on moving, they keep on attaining more and more excited states. So in order to negate their extra excitation, we have to minimize their movement, we have to minimize their excitation. And it is possible to first place 5 electrons into D shell to occupy the partial stability or partial fulfilling of the shell subshells. Likewise, there is a case we can place electron in the way that we can say that we can fulfill that D orbital. When they are fulfilled in the form of in the form of pairs, maybe 2, maybe 4, 5, as per convenience, the more stable they are. So I hope this is clear till this point. If you have any doubts, you can ask us in the comment box. Please hit like button, subscribe to the channel. See you in the next video. Thank you.